What force pulls the apple to the earth? And what force holds the moon in the sky? For 2,000 years, the answer seemed self-evident. They were different forces, separate realms, separate rules. The apple belonged to the world below, the corrupt, imperfect world of change and decay. The moon belonged to the world above, the eternal, divine, unchanging realm of the heavens. As Aristotle had taught, one world sought its natural place, the other moved with perfect purpose in circles divine. For centuries, no one dared to join them. The wall between earth and heaven was absolute. To question it was to question the order of creation itself. But a handful of thinkers, scattered across Europe, began to chip at that ancient wall. And one man, standing among the ruins of their revolution, would build from it a single, seamless cosmos, a universe of law and motion and inevitability. By the end of our last episode, René Descartes had given us a new language, a way to map reality itself. Geometry had become algebra, thought had found coordinates. But a language alone is only potential. Someone still had to write the first true sentence of the modern cosmos. That sentence began with a question from a quiet canon in Poland. In the late 15th century, the accepted picture of the heavens was an intricate machine of circles upon circles. Astronomers traced the wandering stars with a labyrinth of epicycles, mathematical patches meant to preserve Aristotle's perfection. The system worked, barely. It was a mechanical fiction that fit the data but not the soul. Nicolaus Copernicus, studying the heavens from cathedral towers and candle-lit tables, looked at this ungainly cosmos and felt a kind of irritation that bordered on reverence. If creation was divine, should its design not also be simple? He turned the world inside out. What if the earth was not the center at all? What if the sun held court in the middle, and we were merely one of its attendants? With that inversion, the heavens untangled themselves. The strange backward loops of Mars, those cosmic hiccups that had confounded astronomers, became illusions of perspective, born of a moving Earth overtaking its neighbor. The universe suddenly breathed with elegance. Yet Copernicus was cautious. He lived in a world where questioning the heavens could mean questioning theology itself. So he waited. Only in 1543, as he lay on his deathbed, did his great work, On the Revolutions of the Celestial Spheres, finally appear in print. Even then, he kept one foot in the old order. His planets still moved in perfect circles. He had shifted the center of the cosmos, but not yet its perfection. The sun had replaced the earth, but the old geometry still ruled the sky. Half a century later, in a cold German study, Johannes Kepler took up the problem Copernicus had left behind. Kepler was not only a mathematician, he was a mystic of proportion. He believed that God had written the universe in geometry, that the orbits of planets echoed the harmony of musical notes, that every distance in space sang with divine reason. And yet, the data refused to sing. From his mentor Tycho Brahe, he inherited decades of meticulous planetary observations, numbers more precise than any before them. But when he tried to fit Mars into a perfect circle, it rebelled. No matter how he twisted the geometry, the red planet strayed by 8 stubborn arc minutes. Most would have blamed the instruments. Kepler blamed himself, and then listened harder. After 10 years of relentless calculation, he made the leap that shattered the last crystal sphere. What if the orbit was not a circle at all? What if the planets moved in ellipses, stretched circles, with the sun resting off-center, not enthroned in perfection but offset, dynamic, alive? He plotted the numbers again. This time, they fit like a lock and key. The universe, at last, was not perfect, but it was true. From that revelation came his 3 great laws of planetary motion: that planets sweep equal areas in equal times, that their speeds quicken as they fall toward the sun, and that their years grow longer the farther they roam. The heavens had yielded to number. Kepler had shown that celestial grace could arise from imperfection, that beauty was not symmetry, but law. Yet his world remained divided. Above, the planets traced their elegant ellipses. Below, stones still fell for Aristotle's reasons, seeking the natural place. The unification of heaven and earth waited for a different kind of vision. That vision belonged to Galileo Galilei. Where Kepler calculated, Galileo looked. He took a simple Dutch invention, a tube of glass and metal, and turned it toward the night sky. In 1609, the universe revealed its scars. He saw mountains and valleys on the moon, imperfections that mocked the old doctrine of heavenly purity. He saw dark spots crawling across the sun, proving that even the great light of day changed and decayed. He watched 4 small moons circling Jupiter, a miniature solar system in rebellion against Earth's supremacy. And he traced the phases of Venus, waxing and waning just as Copernicus had predicted, orbiting the sun. The heavens were not divine spheres of crystal. They were made of the same stuff as Earth, rough, heavy, and real. But Galileo's revolution did not stop at the sky. On Earth, he performed experiments that were as elegant as they were simple. Rolling balls down inclined planes, timing their descent with water clocks and heartbeats, he discovered that falling objects accelerated at a constant rate, and that motion, once begun, continued unless interrupted. Where Aristotle had seen purpose, Galileo saw pattern. Where the ancients had spoken of natural motion, he spoke of inertia and acceleration. Mathematics, for him, was not decoration, it was the grammar of reality itself. Numbers were how nature spoke, and the telescope was its punctuation. Galileo's defiance of dogma would earn him the wrath of the church, but his equations endured. He had brought the laws of heaven down to earth. And then, silence. A generation later, the torch passed to a solitary mind who would merge all these discoveries into a single vision. In 1665, as the Great Plague swept through England, a young scholar named Isaac Newton fled the closing walls of Cambridge and returned to his family farm in Woolsthorpe. Cut off from the world, he found another, within himself. In 2 years of isolation, he invented a new branch of mathematics to describe change, calculus. He unraveled the spectrum of light with prisms from his attic window. And he began to wonder, could the same invisible pull that brings an apple to Earth also hold the moon in its path? He compared their motions, the apple's fall, the moon's curve, and calculated the forces that could sustain each. When he accounted for the distance to the moon, the numbers matched. The force was the same. He called it universal gravitation, a single law binding every object in existence, from the grain of sand to the distant star. In 1687, Newton published the Principia, perhaps the most powerful synthesis in the history of thought. Within its pages lay 3 laws of motion and 1 of gravity, from which, in principle, every motion in the universe could be derived. With those laws, the cosmos became transparent. Kepler's ellipses, Galileo's falling bodies, the tides of the oceans, the paths of comets, all emerged as consequences of the same, immutable mathematics. The universe had become legible. From these few axioms, the modern world was born. Democritus's atoms became Newton's masses, each obeying forces that acted across the void. Euclid's infinite geometry and Descartes' coordinates fused into absolute space, rigid, eternal, unmoving. Time, too, was stripped of human subjectivity. It became absolute, the uniform ticking of a cosmic clock. The result was breathtaking in scope and chilling in implication. If one could know the position and momentum of every object in this grand machine, one could, in principle, predict every future and retrodict every past. The universe was no longer a story, it was an equation. No will, no purpose, only cause and effect, stretching backward and forward through eternity. Newton's cosmos was the triumph of the it, a universe that ran by the mind of God, yet no longer required his hand to turn the gears. And for more than 2 centuries, this clockwork would define reality itself. What is the world made of? For Newton, the answer was clear: matter and motion, governed by universal law. This vision built our engines, launched our rockets, and shaped the very logic of modern thought. But in its perfection, something was missing. A machine can describe how, but it cannot tell us why. Even in the midst of Newton's triumph, a few restless minds began to sense the absence, to wonder whether nature might choose, whether the universe might prefer certain paths. In the next episode, we meet those thinkers, from Maupertuis to Euler and beyond, who sought not just the laws of motion, but the reasons behind them. The principle was simple, yet profound, that nature always acts in the most efficient way possible. It was called the principle of least action, and it would open the first crack in Newton's perfect clockwork. Until then, keep questioning the fabric of reality.